No.
I agree. I agree.
Now let us continue. Is it useful example of Faraday's law? Understandable? Huh? Good. Now I will show you a couple more examples later, not now. So, due to Faraday, we have to make some improvement of our system of equations of fields which we derived before. You remember I wrote you 4 equations, correct? Would you be so kind to tell what before curl electrical field was? It's time to change. Faraday's law tells minus the beta key. No magnetic. If magnetic field does not change with time, we back to our constant electrical field. Correct? Now, still curl B equal mu naught J, divergence E equal delta over epsilon naught, the divergence B equal 0. So when you read this equation, you have to read them. Otherwise you are pure plumber, with all my respect to good plumbers. Understandable? Don't take it personally, please. Because all my life I'm worried not to be plumber. Not to be even in geophysics. Outside, yes. So, what is written here? Faraday's law. What is written here? Biot-Savart law. What is written here? Coulomb's law. What is written here? No magnetic charges. That's all. Simple, simple. Now, so we improved our system of equation electromagnetic field. Let me open your secret. Except shadow method. Except radar method. Except the electrical logging. These equations, 4 equations, that's exactly what we need. No more. All these physical laws and their mathematical form describe all physical and mathematical foundation of all electromagnetic methods, except these 2. Now, let us move forward. So I introduced one new physical law, one more, couple more, and that's all, don't worry. It's nice in elastic waves. We need only 2 physical laws. Who knows in seismology how many physical laws we have to know? But you have to take courses in seismology. What are the 2 basic physical laws in seismology? No. Snell's law, it comes from basics. Snell laws is valid only for geometrical optics, geometrical seismic, for some special case. What are the 2 basic laws? Wave equation. Sorry, I didn't. You told wave equation. I translate for myself. So no. Wave equation already, if you say in electromagnetics curl and divergence are fundamental laws, it's not correct. It's a mathematical form of physical laws. Wave equation came from 2 physical laws. What are these 2 physical laws? And funny thing you do know, but 3-4 more days, say I will depart. But I think I will succeed if I don't tell you half of what I was going to say, but I still will succeed if you will remember rule of game. know, first of all, physical laws. Try to understand from physical laws. In seismics, there are two physical laws. One of them you know extremely well. Let us say all Newton's law, mechanics. First, second, and third. But in effect, sufficient second because from. You remember second Newton's law, by the way? Huh?
Conservation of momentum, is that one of the basic laws?
No, let us return back to mechanical laws. So what is the second Newton's law?
Rate of change of momentum, force.
So rate of change?
Of momentum.
Correct, but rate of change momentum, what is the next? Rate of change of momentum produces what? Second Newton's law of mechanics. What is the first Newton's law of mechanics? Inversion. Close, but everything is correct. But let us formulate the second Newton's law. Acceleration. Exactly. Yes, but it's generalization momentum. What is the second law which we need in the theory of elastic waves to know? Only two. And then you get quickly wave equation. You will get different equations. Only two physical laws. One of them, second, is very similar Ohm's law. What Ohm's law is doing? It connects electrical field with Ohm's law, or not Ohm's law. Electrical field relates with current density, relation between two fields, correct? What is the very known law which looks like almost as Ohm's law, but in seismic? How we call it?
Famous 17th century.
17th century, gentlemen. Sorry?
Yeah.
Hooke's law, exactly. So using these two laws, we built all theory of seismic, P waves and shear waves, and of course not directly from Hooke's law, but Hooke's law is some genetic word which combines all improvement of Hooke's law, but it was started from Hooke. So, the same story here. We have several physical laws. Faraday's law, Pierce-Savart law, Coulomb's law, no masses. Now, that's not end of the story. Let us consider one more physical law which is important to know in general for theory of electromagnetic field. We discussed this law, but I consider its special case. Now, general case. Flux of current density through closed surface is not equal zero. But what is it? It's equal minus rate of change of charge inside of the volume. It's still principle of charge conservation. You have a surface S. You have a surface S. What this integral shows? Amount of charges which going through closed surface per unit time. Either your charge increases inside or decreases. Therefore, it must be equal to what? For example, suppose amount of charges, let us say, mainly flux negative. It means more charges arrives. Because surface the S as outside. Suppose more charges arrives and less leaves. Therefore, flux will be negative. What would be from physical point of view it will mean? It means charge inside will increase. So it cannot change without additional flux. That's what written here. Suppose more charges leaves, then arrives. Therefore, this flux will be positive. Derivative, negative. What does it mean? Very logical. Amount of charges decreases. So charge cannot be born from nothing. If it changes due to either arrival or departure. So this fundamental physical law has again three forms. Form number one, if you apply for small volume, it will be divergence J equal minus d delta dt. What does it tell you? Exactly the same. Because divergence is a surface integral over volume. Now there is a third form at interfaces. If you apply this integral, you will see that normal component of current density, one side, another side, Gn2 minus Gn1 equal minus density over epsilon naught. Again, three forms. Let us read this equation in order not to make everything too theoretical. What is the meaning of this quantity? Amount of charges which arrives. It's a normal amount of charges which arrives per unit time to the surface. What this quantity means? Which leaves. And it must be only derivative. I forgot to write derivative. The sigma dt, rate of change of surface charge. So let us remember this equation. And now last. That's one more physical law and last physical law and no more. And then we will use them. So this equation, principle of conservation of charge or masses and drive, etc., was known many years ago, at the middle last century. This equation also was derived by Maxwell. And now, only information, because I promised don't write nothing derived. Now, let us look in this equation and second equation. It looks like they contradict each other. That was done by great physicist and mathematician Clerk Maxwell. That was the main achievement. It's not mathematics, it's not physics, it's a story. He had this equation, he knew principle of charge conservation. Mathematics tells, only mathematics, we don't have time to discuss. Divergence from curl is always equal 0. There is such equality in mathematics, divergence, curl of any vector equal 0. That's Maxwell knew. He looked in these two equations, one principle of charge conservation, another Biot-Savart law, and he found discrepancy. And this discrepancy was breakthrough in physics. Additional time shows how easy it was, let us say easy, to make great discovery last century. If you take divergence from both sides, as I told you, on the left side must be 0. Therefore, divergence J must be equal 0. But physicists and Maxwell knew that's not the case. So he wanted to make agreement of this equation with this principle. And artificially, without any experiment, without nothing was known, he told Let me add to right part one more term in such way that this equation will be in good agreement with this equation. So that's story. It's amazing. No complicated mathematics, nothing. Simply, it was moment when Maxwell discovered discrepancy between Biot-Savart law presented in this form and this equation. And he discovered what he had add to right part in order to make this equation in complete agreement with principle of charge conservation. And this term has the following form: plus mu naught epsilon the E the G. If you add to the right part this term, then this both equation will not contradict each other. So it's a story, it's a not scientific discussion, but it reflects fact of the life. And this term, epsilon, the E, the T, let me rewrite this equation. So he assumed it didn't follow from any physical law, unlike previous cases. He assumed that curl B equal mu naught current conduction plus epsilon the E the G. We will not discuss it. It's very simple to show. If that's the case, we will get this equation. And this term got name. What is the name? Who else knows it? Displacement currents. It's as I told you last time, it's impossible to understand physics of electromagnetic fields if we don't know this fact. So, last correction of, now let me rewrite these equations, and we got Maxwell equation. I promised to tell about this part. Mu naught conduction current plus displacement current, where displacement current equal epsilon the E the G. So that's all. That's Maxwell equation. What is written here? Amazingly beautiful symmetry. According first line, what creates electrical field? Rate of change magnetic field with time and charges. Now, what creates magnetic field? Conduction current and displacement currents. Displacement currents. No charge. So magnetic field and electrical are generated by two types of sources. In the case electrical, generate vortex and sources. In case of magnetical, two types of vortexes. Now, we will start to discuss now. Now we will go down from this system to special cases. You have to ask me how this current creates magnetic field. In the same manner as conduction current. Conduction current, so slowly moving charges do create magnetic field, and it turns out when electrical field changes with time, also magnetic field arises. How people know that Maxwell was right? Very quickly, experiments were performed, and there is no one experiment which contradicts genius guess of Maxwell. There is no one experiment. So it was proved by later, by all experiments. For instance, when we watch TV, let us discuss about TV. So, TV station, there is antenna, there is TV set in our room. It's impossible to explain the fact that we watch TV if without this term. Now, light. How we see this light? Only due to this displacement current. How we see each other? Only due to this term. So it's not exercises in mathematics. There is no, it's hard to imagine how we measure our electromagnetic fields, whether we are working in mining, borehole, surface geophysics, without these displacement currents. There are vehicles, there are cars which bring our energy from transmitter to receiver. Without this displacement currents, no way to understand electromagnetics. Even, there is no way even to explain propagation of elastic waves, by the way. But that's a different story. Now, that's Maxwell equations at regular points and similar boundary conditions. 1 times more. What we established, according to this equation, magnetic field is caused by 2 currents. Why they are called currents? You, I, and you like to call currents moving charges because we are accustomed to do it. But how to call currents in free space change of electrical field with time? Only from one point of view it's reasonable to call them currents because they create magnetic field. So what? Current means generator of magnetic field. And it doesn't matter whether electrical field changes with time or charges are moving. So that's all about Maxwell equation. Now let us use this result and move closer to electromagnetic methods. Again, since it's not a serious course for semester, 1 month, I only explain step by step. This system of equation describes all electromagnetic fields, practically all electromagnetic fields. But this system is not pleasant. Even it's a Maxwell system of equations. Why it's not pleasant? This equation, there are here 3 equations which contain derivatives. Here 3 equations which contains derivatives. Here 1 equation contains derivatives. So too many unknowns. So mathematicians solve one simple problem. They decided maybe it's possible to, they thought, maybe it's possible to replace all 4 equations by 1. By 1. And they did it for the special case which of great importance for us, at least. Let us discuss this case. We have so-called piecewise uniform medium. What does it mean? It consists of pieces of volumes where parameter gamma, the electrical constant, magnetic permeability are the same. So here the same, here different but the same, here different by the same. That's piecewise uniform medium. So let me show you what in effect I told you yesterday. In such medium, charges don't arise. No charges. You remember, we demonstrated for constant field, no electrical charges inside. More precisely, density of charges is 0. Let me show you. It's a simple example. It's exception. I will derive it. You will see what would happen. I have two equations which contains charges. Principle of charge conservation and third equation of Maxwell, divergence electrical field equal delta over epsilon naught. One step, second step. Do we have relation between current density and electrical field? How we call this physical law? Ohm's law. Thank you. Ohm's law. Let us replace conductivity by electrical field here. Ohm's law. I write something will be proved today. Divergence gamma electrical field equal minus d delta dt. I replace current density by conductivity in gamma. I consider piecewise uniform medium. It means what happens with conductivity inside of such medium? Does it change or it doesn't change? Constant. So let us take gamma out. Gamma divergence E minus d delta over dt. Do we have expression for divergence? We have gamma delta over epsilon naught equal minus d delta over dt. No more divergence, no more curl. Simple, simple relation. Now, what is it? Derivative of density with respect to time plus gamma over epsilon delta equals 0. Do we know this equation? What is it from mathematical point? It's hard to imagine simply. That's the reason why I brought your attention. What is it? Differential equation of which order? First order. Do we know solution of it? Mathematician, where are mathematicians? Can you tell me what is the solution of this equation? Some constant, and then it's a first simplest example, but very important in understanding on field. Let me tell you, it will be exponent minus t over tau. That's all, where tau is equal epsilon divided by gamma. Take, replace, you will see how it beautifully works. How this parameter is called? Is it correct? Let us check it. Maybe I'm wrong. I think it's correct. Time constant. So it tells you if you place, we never do it, but it's not too bad to imagine, if you place charge in our rocks, it will exponentially decay very quickly. Really quickly? Who knows? We'll check it. Its decay depends on time constant. What is the time constant? Let us write down. Time constant equal epsilon rho. Epsilon times rho. What is the dielectrical constant of the rocks? Let me help you. It is equal epsilon r, relative dielectrical constant. We discussed yesterday. Somebody asked me what does dielectric mean. Now, times dielectrical constant epsilon naught, which is equal unit divide 35, 10 minus 9 farad per meter times rho. Yes, it's correct. So, time constant is equal let us take clay or sand, 10 units. Epsilon r equal 10 units. And let us take resistivity 20 ohmmeters. So what we have? 10, very small number. So it's unit divide 2, 10 minus 11 times 20. Don't forget it's a second. It's a second. So what we have? 10 minus 9 second, or 1 nanosecond. So practically we are measuring always much later. So if you place charge, it's equal constant, some charge at the first moment, minus t over 10 minus 9 second. If you take 1 millisecond, what would be the value of the charge? Here 10 minus 9. Here take 1 millisecond. Big or small? If you take 1 nanosecond, then what happens? Physical meaning of this quantity charge when time equals 0, initial charge. So if you take 1 nanosecond, what happens with charge? It will be decreased in how many times approximately? 3 times. Let me write again. Delta equal delta naught E minus T 1 nanosecond. So if T equal 1 nanosecond, it will be ray E minus 1. Take 10 nanosecond. E power minus 10, small number? Awfully small number. So each time when charge is placed into medium, it quickly disappears in our cases. So that's the reason why this Maxwell equation greatly simplifies, tells in uniform part of the medium, no charges. That's what we established last time. This equation is very important, but it's applied only for inside of layers. But at interfaces, we do still have charges if there is a normal component electrical field. So, Peter, when we have break? I forgot 5 minutes. Very good. Very good. So, after this small information, so this equation, we need to simplify this equation because then we are close to reality. No charges inside, only at interfaces. Now, back to achievement of mathematicians. taking into account that this system of equation is extremely complicated, mathematicians replace this system by one equation. Only one equation. And we, are geophysicists, should know this equation because it contains all physical laws, as wave equation contains Newton's and Hooke's law. The same equation we have in our electromagnetic matters, where Coulomb's law, Biot-Savart law, displacement currents, Faraday's law, all of them there. So this is a step number 3. And that's, I will write this equation, tell a few words, and we will start to consider some special cases after break. Let me show who knows this equation. Very good, I will tell you. I will feel more comfortable. I don't like to tell what you know, it's unfair. So, this equation, there was very famous mathematician D'Alembert. Mathematicians know this equation, mathematics. This equation has the following form. Laplacian, that's Laplacian, I will remind you again what is it, is equal plus gamma mu, clear what does gamma mean? Conductivity, mu magnetic permeability, first derivative plus mu epsilon, second derivative, equal 0. For those who forgot what does it mean, let me tell you. For example, Cartesian system of coordinates. Cartesian system coordinates. Laplacian is symbol which shows take second derivative with respect to x, I'm sorry, plus what? From y, correct. Second derivative from y. Take second derivative from z, that's your Laplacian. So this equation is analogy, is another phase of Maxwell equation. And it describes all possible cases. It tells you behavior of all electromagnetic fields, radiotechnic, TV, communication, geophysics, inside of electronics devices, everywhere, without any exception. So we have system of Maxwell equation, and we have one equation, and similar equation for magnetic field, exactly the same. Exactly the same. Gamma mu dB dt plus mu epsilon b dt. These two equations tell us about all phenomena which takes place in our geophysics, electromagnetic geophysics, without any exception, everywhere. If, for example, direct current, remove all derivatives, that's it. And then, after break, I will start step by step to tell you about propagation, diffusion, quasi-stationary field, and consider example from our practice. So in order to finish, let me tell you, inside of this equation, Coulomb's law, Faraday's law, Biot-Savart law, the displacement currents, everything is here. Now, but I think what my idea, I cherish my idea that companies, advanced, good companies, the managers of the companies, presidents, senior geophysicists, have to find a way to convince board of directors, in the case one board of directors. So they have to pay their employers at least half or 75% of the book. So there is something.
They're allowed to read my
Yes, I understand. Now, let me read that gave me one advice. I was lazy, I didn't do it. And I would like to follow his advice to tell you to return back to displacement currents and give you another explanation why we have to introduce displacement currents. Let me show. It's a classical example. In each textbook it's written. So let me do it. And then we will return back to our equation. I am sure some of you saw this example. I didn't see one textbook in physics which does not contain this example. Example is contour with condenser. Contour with condenser. Current contour, condenser, generator. Now, there is a current ampere meter, for example, 1 ampere, correct? Now, do you agree there is a current if it's alternating current? Ampere meter must show a result. So there is something between inside of condenser. Even condenser is not material is not conductive. It must be something. So this something is displacement current. Now, its density of this displacement current exactly equal epsilon d dt. If you take this density, you will find out the total current equal this current. Now, we remember Ampere's law. Ampere's law tells you take contour around wire. BDL along this contour is equal mu naught times what? Please remind me, we discussed today. Current. What is the current? Current which going through any surface S bounded by this contour. This surface S. Clear? So you take this contour. What is the current goes through this surface? I. You take this surface, current I. So integral all time the same, equal mu naught times current. Then trouble. Let us take this surface mentally, which is going through condenser. Of course, this result must be the same. But what is the current, conduction current through condenser? Nothing. No ions, no electrons. So in order to make this result the same, we have to assume there is another current here, which magnitude of which is the same as conduction current. And this current is called displacement current. So there are different now ways to prove it, but Maxwell still was genius. He didn't know this example, any example, he realized it. Now back to another form of Maxwell equations. And let us discuss this equation. Everything, all phenomenon here, we start from first phenomenon. First, there are several phenomena in electromagnetic fields. One, propagation. Second, diffusion. So let us understand propagation and let us understand diffusion. All these equations tell you about propagation and diffusion. Let me assume very simple. I have only one tool. We have this equation. Let us read this equation. What does it tell us? So let us start from simple case. Case number one. Please imagine some plate, metal plate. Very large. Very, very large. Now, please imagine current goes along axis Z. Current. How they changes with time doesn't matter. Let us write Jz equals Jz naught times function of time. Clear? So please imagine metal plate. Everywhere currents goes in this direction. Is it understandable? Now, let us ask ourselves, what happens around this plate? Let us take, that's axis Z, axis X, somewhere axis Y, we are not worried about it. Let us look at this equation. First of all, this equation valid everywhere. We consider very simple case, air. Air. So what happens with this term? 0. Then let us assume, since currents goes this way, magnetic field will have each component. We have to make everything as simple as possible. Perpendicular. By Biot-Savart law. So instead of this monster, we will get much simpler equation. First of all, we assume magnetic field has only one component. So let me write it. Let us assume magnetic field has only component By, and it does not depend on axis Z, axis Y, since we consider very large plate. Nothing changes in all these directions. Therefore, this equation becomes dBy dx squared. What is it, by the way? Which term? That's term. Because no derivative with respect to other components, no other components. Plus, do we have this term? Yes. Mu epsilon the By. Seconds, I think I made a mistake. Yes, of course I made a mistake. I'm sorry. Here minus. My God. Minus, and I hope here also minus. Yes, please correct. I sorry, everywhere minus. Here, minus dt the square equal 0. Please, where plus put minus. So I mechanically put plus. So that happens with our D'Alembert equation. How we call this equation? Wave equation. You see? So first, what we discover, our D'Alembert equation becomes wave equation. Now, why it's called wave equation? Now we approach, again, engineers should know. So something wrong here? Huh?
I don't understand why it's a By check.
Sorry?
Yeah, By.
Because if current goes in this way, magnetic field has only perpendicular component. Now, it's the most simple case. This equation has a name. It's wave equation. Why it's called wave equation? First of all, do we have in this case conduction current outside of this plate? No. Correct? Because it's a free space. Or insulator, it's better to say. So at each point there is epsilon, but gamma equals 0. Mu, epsilon, gamma equals 0. Now, what else we have? if we don't have conduction currents, how magnetic field could arise? Huh? Only due to displacement current. So we have only displacement current. Now, let us look, what is the solution of this equation? Without any proof, there is its known fact. As soon as you have this equation, solution has the following form. By equal b naught y function, any function, this function, which is equal t minus x over c, where c is equal x, c, just not x, sorry, c equal unit divide square root epsilon mu. What is written here? Let us discuss. If that's what we always observe in electromagnetic methods. What this combination mean? Time minus distance over velocity. C is the velocity of electromagnetic waves. It's equal unit divide square epsilon mu, and if it's a free space, it's equal velocity of light. What is the velocity of light? 10.8 meter per second. If it's dielectric, water, what happens with velocity? Huh? How? Correct? Slow down 9 times. But what is amazing, in conducting medium also it will be the same expression as in non-conducting medium. Velocity of propagation will be defined by this term. So if you turn on transmitter, your dipole, for example, in time domain, you will observe this propagation. Part of energy will go over through air, part through medium. The part of the energy which travels through air will go with speed of light. Part of the energy which goes through conducting medium will travel with velocity slower, because the electrical constant is not 1. Now, let us read this equation. But this, just a second. Let me write it. Let me write separately this function. T minus x minus c. What is it? Argument of this function combination, certain combination between time and x. T minus x minus c. For instance, sinus omega t minus xc. What does it show? Let us think together. At some moment t, 1 second, and x equal 100 meters, this argument has value 1. Tell me please, if I take x greater, when I will have the same argument 1? It's not clear? No problem, I will repeat. Again, let me call t minus xc u. U equal t minus xc, function f u. This function, our field, does not depend separately on time on x. It's defined by this argument, u. Suppose u for x equal 100 meters and t equal 1 second, u equals some number, u1. Tell me please, if I take greater distance of x, when u will be again equal u1? Sorry? At some greater time. If you increase x, so you have pair of time and x, when argument equals u1. Then, if you would like to know when function will have the same argument and therefore the same value for greater x, when it happens, when time will be greater. Now you would like to find another point x where function will have the same value. Again, you have to take greater times. So what does it tell? This clever equation tells you that given value appears later and greater times. It means what? Travels. How quickly it travels? With velocity c. If you tell yourself x1 minus t1 divided c, that's your argument. When you will have the same argument at greater times, you have to write x2 minus t2 divided by s. If you take x1 in one side, time another side, you will get what? Delta x equal take. Oh, wait, I did mistake. Sorry. T1 minus x1 over c equal T2 minus x2 over c. That's our argument. Let us take T1 on the right side, x2 another side. What we will get? Delta x over c equal delta t. So, what is the meaning of c? Velocity. That's the reason why this equation is called wave equation. For instance, my current, let us discuss now in detail. My current changes as function of ft. Arbitrary function. It could be impulse, step function, what you would like. If I take point very, very close, what is our argument for magnetic field? Let us write again. By equal b naught function t minus xc. If I take x very, very small, very close to the plate, how our magnetic field will change? So let me show you again. That's current is z, some function t. Now my question, if you take point very close to the plate, how will magnetic field By change? Huh? Practically the same. Take x 10 minus 20. So this term will be very small, so practically synchronic. Now take time, take distance greater. What would happen? That's magnetic field. Now x1, far away. What would be behavior of magnetic field? What letter F mean? Huh? Arbitrary function. Does it change shape of this function with distance? For instance, I wrote you, it could be by equal b naught e minus some parameter alpha t minus xc. Regardless what is the time, regardless what is the distance, function is the same. Shape is the same. That's, I consider, special case in order to illustrate concept of propagation. So, could you help me to plot graph of the function at greater distance, magnetic field, not function, magnetic field.
Move it down and move it to the right.
Hmm?
Move it to the right.
Move it to the right, correct. Correct? Now you take great X, you will see it later. So this wave is moving. Field is moving. That's what happens with stars. Stars, there is explosion, they create wave, electromagnetic wave, light, it starts to move. Light could be already dead, but wave is moving and moving and moving until it arrives. Now, can we use Biot-Savart law? No. Why? What Biot-Savart law tells us, or Coulomb's law, tells us if current changes as function of t, current, then magnetic field must change how? In the same way. Because Coulomb's law, Biot-Savart law, completely neglect propagation. Now, so if we have some constant Ft, the same for charges, phi t, electrical field, according to Coulomb law, has the same constant. So here, phenomenon of propagation. We always have it. Different story. Do we observe it or we don't observe it? In all time domain frequency methods, we don't see it. But an energy cannot arrive instantly. It propagates with velocity of light or a little slow. Now, how it happens? Let us discuss approximately how it happens. I wrote equation for magnetic field, but there is the same equation for electrical field. So our equation for magnetic field, By the z square equal unit divide c square by the t square, and there is similar equation, only electrical field has component Ez along current, exactly the same. So at each point there is electrical field and there is magnetic field. Ez, Ey. Energy travels in this direction. So there are two currents. No, two generators, I'm sorry. Two generators. What is the generator number one? Rate of change magnetic field with time. What does it create? Electrical field. We have another generator of electromagnetic field, DEZ. The T, what does it create? times epsilon. Magnetic field. So at each point we have two generators. Electrical field changes with time. It creates magnetic field. Magnetic field changes with time, creates electrical field. They support each other. In this way, wave travels. Now, let me ask you one question. Let me check how you understood me. Suppose that's, let me take x is z, let me take magnetic field By, let me fix, consider moment t equal t1. Wave propagates. Suppose shape of the wave has the following form. Clear? Now, let me consider another dependence. Here time, here By, and I would like to fix, oh, I'm sorry, not z, but x. X. Now, let us fix x equal x2 or x1, doesn't matter. What would be the shape of the wave? So again, wave propagates, magnetic field, they behave in this way. So at some moment, that's value of magnetic field at point x1, that's point x2, x3, x4, x5, etc. Then nothing. That's front. Now, I would like to consider opposite case. Suppose I fixed moment and my receiver measures field. What would be picture? What comes first? What comes later? Huh? So first will arrive this front. Then always vice versa. Why it's vice versa? When you look in this graph, you see this front already far away, relatively far away. How it could happen? It means it arose early. That's what you see here. Now, let me find out how long it takes for waves to travel in our electromagnetic methods. What is the, usually we have size of the loop? Couple 100 meters maximum. Huh? Is it okay? Now, that's receiver. That's transmitter. Suppose you turn off your current, or turn off or turn on, doesn't matter. So energy starts to propagate. When it arrives, when front arrives an observation point, let us find out what is it. C will be equal to 200 meters divided by what? Speed of the light. 310.8 meter per second. So we have 2, 3, it's 1, doesn't matter, 10 minus 6 meter per second. Oh, sorry, 10 minus 6 second. 1 microsecond. Too quickly. Usually we start to measure later. So we all, in order to get signal, it must propagate. It must. But fortunately for us, we start to measure for such arrays later. And therefore we don't see this first arrival. We measure what happens after. So let us distinguish. Always, in order to get signal, it must propagate. On the other hand, we don't observe it for almost all methods, except again radar systems. We measure later. Our receiver sleeps when signal arrives. That's physical part of this story. Now, F is very good. Now, what is interesting? I have transmitter, that's Earth surface. Here our ore body. When signal appears here, again we have to take distance, divide by speed, and find out. And again we will find out it comes too quickly, and our receiver does not measure. Now, let us look in this fact from different point of view. That's our transmitter. That's our observation point, P1, P2, P3, P4. At each point, signal defines by approximately this function, time minus r distance over velocity. Now, here R1, here signal minus R2, C, etc., where it's R1, R2, R3, R4. Let me ask you a question. Signal arrives simultaneously or not? Pretty close, but not simultaneous. Now, if this time is extremely small with respect to time, first time when we measure signal, what we can say about these terms? Huh? Sorry? Small. Can we neglect? For example, if it's we start to measure from millisecond, I hear only 10 microseconds. In reality, signal does not arrive simultaneously. But taking into account the fact that we measure much later than signal arrives, we can bravely neglect by this term. Simple receiver sleeps. Again, receiver sleeps when signal arrives, front arrives as a seismic. No different. Exactly in seismic. Arrives, there is a front, but unfortunately too quickly. And therefore, if you have receivers at all these points, which starts to measure later, essentially later than first arrival, you can say signal arrives, properly to say, simultaneously. It's proper, understandable. That's reality of all electromagnetic method, again, except radar system. So, again, it's not exact explanation. I simplify, but idea is here. So each time when we can neglect time of arrival of signals, it means we assume that signal arrives simultaneously. Such electromagnetic field has name. Who knows? Quasi-stationary field. And all theory of time domain frequency methods is based on assumption that we deal with quasi-stationary field. Now, it means we assume, everywhere we assume signal arrives simultaneously. We don't care what is the value, but fact that signal arrives, it's wrong. It's a disaster from physical point of view. But we don't see this range of time. I will come back to this concept when I consider conducting medium. But it means we measure later, and receiver does not tell us anything what happens before. So each time when magnetic field, just a second, let me write, B point P equal B naught times FC, function the same. No, these terms is absent. This field is called quasi-stationary. Now, tell me please, if we forget about my speculation, my explanation, attack this problem from mathematical point of view, how to get rid from this term? What has to be put equal infinity? Distance we cannot put in infinity because we measure in a distance 200-300 meters, it's small. But what has to be made infinity in order to get rid of this term? Speed. Speed. So quasi-stationary field means that we assume the speed of propagation is infinite. Now, but what does it mean, speed propagation infinite? What physical parameter is neglected? Just a moment, let us write term epsilon mu. Not. Which parameter should be put equal 0 if we would like to assume that speed infinite? Epsilon. If you assume epsilon equals 0, then you will get, if epsilon equals 0, which term, which current is neglected? Displacement current, because displacement current is epsilon dE dt. So what happens with our system of equation? It becomes nice, old, pleasant, and no influence the electrical constant. So, using different languages, we come to the same point. For all practical purposes in time domain and frequency methods, we assume signal arrives instantly, simultaneously at all points. It's not true, but difference is extremely small and we are not able to detect. We would be able to detect if we changed our receivers. They start to measure from parts of nanoseconds. Then you will see everything. It will be a beautiful story. Even I will tell you what would happen. Sometimes your receiver will keep silence. Even it starts to measure from 0. Why it will keep silence? Time of arrival. The signal didn't arrive during some time. So then your receiver will see first arrival. Then it will be some another time. And then finally you will see simultaneous arrival of all signals. Several stages we don't see using our receivers. In order to get rid of, don't think about them, we blindly say, we assume signal arrives simultaneously, or we say no influence of displacement current, or we neglect by propagation effect. I think it's time, huh? Or not yet? We have time, how many minutes? Excellent, excellent, because I would like to finish it. Is it clear? Clear? Good. Now, let's be logical. If we neglected by displacement currents and are going from this moment to deal to the end with our real quasi-stationary field, let us again write system of equations. Please help me. What happens with first equation? Whether we have displacement current or don't we have displacement current, what this equation tells us? Electrical field is caused by change of magnetic field with time. So this equation is the same. What about now important point? What is the happens with second equation? Let us read each equation without second term. We get rid of it. How we derive this equation? Let us be logical. What is the physical law which was used to derive this equation? By Biot-Savart law. So, let us write for a moment this equation. That's current density at each point. So, current density changes with time. Arbitrary, sinusoid, exponent, or as you wish, logarithm, as you wish. Tell me please, if function current density at some point changes as function of Ft, how will change magnetic field caused by this current? You understand my question? At this point, current changes as function some Ft, sinus omega t. How magnetic field will change due to this current? That's true, but the same function or different? No. Stop. So, Biot-Savart law, magnetic field, total magnetic field is equal integral from. Now, if I would like to take one current, I am asking you, one current. At the depth 20 meters beneath Earth's surface, I have some current. Can I say magnetic field caused by this current is equal J, some point Q, LQP cube dV. If J at some point changes function Ft, sinus omega t, what we can say about dependence on magnetic field? The same. So it will change the same as in direct current. So instantly everything happens. At some point current equals 0. Therefore magnetic field somewhere due to this current will be 0. If current at this point reach maximum, exactly maximum will be magnetic field due to this current. Clear? So shortly, in quasi-stationary field, magnetic field changes exactly the same manner as current. And Biot-Savart law is valid. Couple minutes more. Now, the same is true for Coulomb's law. Now, what happens with our lovely D'Alembert equation? Let us look in our lovely D'Alembert equation if we neglect it by displacement currents. Here divergence C equals 0, divergence B equals 0. That's system equation quasi-stationary field. But what about the Lambert equation? Can you dictate me, please? Laplacian B minus no, the Lambert equation. Conductivity times mu. What is here? First derivative equal 0. How do we call this equation? Diffusion or heat equation. That's our mathematical foundation of all electromagnetic methods. So when we have quasi-stationary field, we have this system of equation which tells electrical field can be caused by charges at interfaces plus rate of change magnetic field with time. Magnetic field is caused by only conduction current. But if you would like to understand our phenomenon, it's not too bad to say this system of equation as described by heat equation. So our methods, basis, mathematical basis, diffusion equation. Why it's called diffusion equation? Or why it's called heat equation? Well, propagation, it's clear, wave equation, because wave describes propagation of waves. Why all our methods, practically all our methods, are described by diffusion or heat equation? What do you think? And then we will go back. That's the end of our theory. Diffusion and heat.
Those things change with time.
But in wave equation also changes with time. Correct? When we consider propagation, our field also changes with time. But there is a fundamental difference between heat equation and diffusion equation. Both phenomena are basis of all electromagnetic methods. Only one of them happens so quickly we don't see. It's our train, wave phenomenon. It's a train it's a vehicle which brings our energy to the observation point, but itself we don't see it. But what we see, diffusion. Why it's called diffusion? If you start to watch what happens with ions in solution when you create high area of high concentration and low, you will see the density of ions changes in such way that it describes by diffusion of ions. Now, why it's called heat equation? If you take medium, and the medium creates source of the heat, you will see that heat will change from point to point, but not as propagation, as diffusion heat equation tells you. So when we deal with behavior of the heat, we use this equation, we call it heat equation. When we deal with describe motion of ions in different parts of solution of medium, we know it's described again by the same equation. It's called heat equation. And we use this equation for our quasi-stationary fields. Let us stop here.